SwayamPrabha. Digital India. Educated India.
Last time we have discussed the laser welding processes and the basic principle of the lasers and the source of the laser, how we can apply in the different welding processes. Now, we will shift to that another part of the laser welding process, that is called laser assisted hybrid welding. So, hybridization of the laser welding processes has been started long before, but of course, there are certain advantage of hybridizing of these laser welding processes. So, basic idea of the hybrid laser welding processes is the sense that another secondary heat source actually is added along with the primary heat source as a laser. So, we can get certain advantage in this process in that in other way. That first main advantage is that we can create the large weld pool volume in general, because application of the laser actually focus concentrate on the very small zone, and normally it creates the keyhole formation, that means keyhole mode welding processes, but at the same time added heat source from the any arc welding process helps in the several way. Probably that arc welding process increases the width of the heat affected zone or molten zone. So, therefore, if there is a need for to create large volume and of welding zone is required, then hybrid laser welding process is one of the most solution. But the main concern in this case is that how this arc is interacting with the laser, and both way it is benefited with respect to each other. In that means that arc actually facilitate the formation of the keyhole, and at the same time keyhole also try to help to stabilize the arc by providing the extra heat energy within the zone of interest. Now, primarily we can see that there are several other arc welding processes like the TIG welding or gas tungsten arc welding processes, plasma, and then laser with the gas metal arc welding. These are the typical secondary sources of the heat in case of hybrid laser welding process. But the question is that when you try to develop any hybrid laser welding processes, what should be the position of the laser, whether it is in the front side or whether it is back side with respect to the welding direction. Now, in principle of the laser assisted hybrid welding process, we see that combination of the gas or solid state, mostly CO2 laser, Nd:YAG laser, or nowadays fiber laser, can be joined with other arc welding processes like gas tungsten arc welding process, gas metal arc welding process, and plasma arc welding processes that actually supply the secondary energy source in the hybrid process. Now, again we can do the further differentiation that the secondary heat source without the material addition or with the material addition. For example, that gas tungsten arc welding and plasma arc welding process is used without any material addition, but gas metal arc welding process there is some material addition along with the laser welding process. So, therefore, when there is a consider the material addition, that process becomes more complex. So, analysis may not be very straightforward, because there are several interaction of the material deposition, interaction between the arc and laser is always a complex phenomenon. So, let us see how this process is helpful in industrial practice, but we will look into that basic advantages or basics of this laser hybrid welding process in this course. So, first focused laser beam actually impinges on the workpiece surface, and that may cause the vaporization of the workpiece material, and the workpiece material actually finally form a vapor filled keyhole. That means basically the keyhole mode is mostly usable in hybrid laser welding process. Now, the power of the arc actually in the arc welding process, that actually introduces the more amount of the energy, and the laser actually helps the process of the gas to be ionized, and in that sense it laser actually enhances the arc stability in the hybrid welding process. So, that means the laser helps in the formation of the arc and their stability in this process. But if you look into other way also, that arc also helps in the sense that by increasing the laser beam absorption, specifically when there is a highly reflective material we try to weld. So, in highly reflective material like aluminum is actually beneficial when you use the laser assisted hybrid welding process. Another specific principle it follows, that hybrid welding process there is a increment of the weld penetration, basically high depth of penetration we can achieve using this hybrid welding process, and at the same time the welding speed, high welding speed can also be used in this case as compared to the individual processes. That means, as compared to the if we compare with respect to the individual laser welding processes or any arc welding processes. So, in the sense both way it is advantageous in terms of the creation of the high depth of penetration, and probably we can use relatively higher welding speed that may have limitation in case of individual processes. So, if we classify the hybrid welding processes on the basis of the heat source, so it can be divided into two things. One is the secondary heat source, another is the primary heat sources. So, of course, primary heat sources, that carbon dioxide laser, NDOAC laser and fiber laser, these are the primary source, that means it is a basic laser welding processes, and secondary source can be arc welding processes that we have already discussed, that several arc welding processes, GTA, gas tungsten arc welding processes, gas metal arc welding processes, and mainly plasma arc welding processes. These are the main processes we use in hybrid laser welding system. But heat source can be of other types of the heat source can also be used in case of the laser assisted hybrid welding processes. Just we can see one example, that hybrid laser brazing processes. So, in case of hybrid laser brazing processes, generally resistance heatings between the part and the wire, brazed wire, we are supposed to use this wire. So, that resistance heating occurs within the wire, and that actually increases the temperature of the wire. But at the same time a laser actually melts that brazed wire, and as well as is supply the heat to the base material. So, these are the typical mechanism of the hybrid laser brazing process, and we can categorize as that apart from the arc welding processes, the hybrid laser welding processes also developed using the other heat sources. Here the other heat sources is that the due to the resistance heating. Now, if we analyze, if we see that overall benefits of the hybrid laser welding processes with respect to the conventional welding processes, we can define few points. That first point is that it is a very high efficiency process. So, around 80% efficiency as compared to the individual processes. So, that is the main advantage. Second advantage is that if the practical situation arises that there is a large gap between the two substrate or two workpiece materials. So, in this case the hybrid laser welding probably is a very good solution to join the material, because in the hybrid laser welding process join the material either without using any third material or then without any metal deposition, or using the some other material deposition process to fill the gaps. Because in this case the hybrid welding process, the volume of the oil pool is relatively more as compared to the laser welding process and even as compared to the laser welding processes, because here the arc welding basically try to increase the surface area of the fusion zone, and laser welding helps to create the large penetration in this case. So, large, when there exists some large gap, probably this is the advantageous using the laser assisted hybrid welding processes. And of course, very high thickness materials can be joined using these hybrid processes. Other processes is that slow cooling rate. If we use the relatively low welding speed, and in that case that high input per unit length, if it is very high, so in this case it follows the rate of cooling is very slow in this case. So, that slow cooling rate actually helps us in the to structurally stable weld joint material can be produced based on this. Then another advantage of hybrid laser welding process is that for highly reflective material. So, probably when you use the individual processes, either laser or arc welding processes, it is very difficult to join the highly reflective material like aluminum. But with the use of the hybrid processes, probably it is the advantageous, or it is not too much difficult to weld of this kind of material. And another point of benefit using the laser assisted welding process, that metallurgy of the metallurgical structure of the weld joint can be adjusted, and at the same time the large gap can be filled by adding of the filler material. So, these are the typical advantages of the laser assisted hybrid welding processes. We can look into the other part of the laser assisted hybrid welding processes, that what are the different factors that actually affects the metallurgical structure, and of course, the mechanical properties also depends on the metallurgical structure of the weld in presence of the material addition. That means, when we merge or maybe when you create the laser assisted hybrid welding process using the laser as well as the gas metal arc welding process, which is different from the plasma or other arc welding processes, because here there is a material deposition in case of gas metal arc welding process. So, if you see from the figure that there is a several interaction. First interaction is the material addition to the domain, and laser actually creates the large depth of penetration, and of course, it follows the keyhole mode welding process. So, there is some metal vapor will be there, and that there is a maybe typical size of the liquid melt, and of course, the solidified size, and in this complex interaction is really very difficult to analyze, but if you see keep in the few points on this type of hybrid laser welding processes. First point is that there is a formation of the plasma formation, and of course, that plasma formation actually affects the metal transfer phenomena, and ultimately it affects the weld pool dynamics. Second point is that laser induced plasma formation and the laser plasma interaction becomes more complex in this case. So, that the interaction actually helps to the absorption of the energy during the welding processes. Second point is that recoil pressure and other possible phenomena considering the formation of the weld pool dynamics, basically the influence of the here the any kind of shielding gas that creates the more complicacy in this process. And of course, finally, the plasma filler metal weld pool interaction also becomes another factor of complexity, and that is it's difficult to analyze all the effect of the individual phenomena in a straightforward way. So, I am not going into much details about how they interact with respect to each other, but rather we will try to just point out these are the typical situation that may arise during the interaction of the laser and the other gas laser and other any kind of arc welding processes that may happens in the development of the hybrid laser assisted hybrid welding processes. Now, in general, if we try to analyze that what are the influences of the hybrid welding process parameters and on specific to the bead shape. So, the bead shape also influenced in general by the different parameters. First is that distance between the arc and laser beam. So, between the laser beam and arc, if it is too close with respect to each other, that deeper penetration is assumed. So, compact effect the arc and laser will be more, and in this case probably we can relatively narrow heat affected zone or narrow weld zone we can expect if the arc and laser beam are close to each other. If they are far away, the effect or may not be beneficial. So, in that sense, so smaller the distance, so we can achieve more depth of penetration. Second point is that position of the laser beam, whether we can put in the front, or whether it is laser can be put in the front or laser can be put in the backward side during the welding process. And in this case, if we put the laser beam that in front of the arc, that is more preferred way, specifically when we try to make the hybridizing of the process using laser and gas metal arc welding process, because gas flow does not actually affect the molten pool created by the arc, but shape of the bed surface is basically disrupted by the acid gas blowing into the molten pool. So, normally in case of gas metal arc welding process used for the hybridizing of the laser processes. So, in this case the laser is kept at the front side and the gas metal arc welding put in the backward side. Another effect of the hybrid process, that is the effect of the arc power. So, in GMAW laser assisted GMAW process, in this case that at constant wire, keeping the constant wire feed rate and we keep it the laser power as a constant. So, basically increasing the arc power, that actually increases the width of the weld zone. That is also obvious, because arc power in this case the helps to creates the wide widthness of the weld pool volume. And of course, laser in the, because laser is used to increase the depth of penetration and the purpose of using the arc is width. So, using the arc power, definitely it will try to create the on the top surface the size of the weld pool weld volume will be more. Now, we covered about the laser welding processes and the of course hybridizing of the laser welding process also we have discussed. Now, we will try to focus on the electron beam welding process. This is another high power where we can use the high power beam energy, and this is the electron beam welding process, one of the most precision welding processes and of course, one of the most costly processes. So, we will try to discuss this electron beam welding process, and of course, we will focus on the basic parts of the electron beam welding process. Electron beam welding, if we see that in this case the high energy density can be created. So, up to 10 to the power 8 watt per meter square, or I think it should be centimeter square fusion welding processes. And if you see that basic principle of the electron beam welding process, that if it is possible to create the beam of the electrons, that can be done by the bombardment of the intense beam and of electrons, and that can focus on a specific workpiece. So, that on the workpiece the kinetic energy of the electrons is basically converted to the heat energy or maybe converted to the thermal energy, and that thermal energy creates the a weld pool weld volume, and of course, here also formation of the keyhole happens. So, in this case the when it creates the weld pool volume, and if you see that due to the bombardment of the electrons to this workpiece surface, and at the same time there is some scattering of the secondary electrons also happens, and the temperature becomes so high. So, thermal radiation also happens, that is the heat loss through the radiation from the oil volume, and it also creates some X-ray. So, there is a creation of the X-ray effect in the electron beam welding processes, but that was not there in laser welding process. Now, of course, when it creates the volume of the molten volume, then at the same time some amount of the heat is conducted through the solid medium workpiece, and within the molten pool there is a convective flow of the material also happens, and at the same time there is also heat loss through thermal radiation also happen. It is remember that electron beam welding generally happens in a vacuum chamber. So, we can do the further on this electron beam welding process, that basically the electron beam gun we used has a tungsten filament. So, that tungsten filament can be heated and to create some pool of electrons. Now, second thing is that after creation of the electrons, it can be accelerated with the from the source with the high voltage. If you keep the high voltage difference within the source, so electron can be accelerated. Now, the stream of electrons is passes through a hole in the anode, so that the beam is then directed by the magnetic forces, and then it is a focusing and then deflecting to a specific point by the focusing on a specific point by the deflecting coils. We will see in details about the what are the typical components of the one simple electron beam welding machines. But finally, the beam is directed out and strikes on the workpiece surface, and of course, the kinetic energy of the electrons is actually transferred to the heat with the impact of the workpiece, and it creates a perfect hole in the weld joint. That means, perfect hole means in the sense it creates the basically one keyhole, and then there is a when the keyhole moves forward, it will fill by the molten metal, and in this way it creates a deep penetration welded structure. So, of course, in this case in principle with respect to the laser welding process, the source energy creating of the energy is different from the laser. But in general, if we see in electron beam welding process, that first is that it should be done on the accelerating creating of the electrons, accelerating and the focusing on the specific point, all done in a chamber, and finally, the welding has done it is within a vacuum chamber, so that it cannot be deflected away in presence of air or in presence of any medium. But in laser welding, probably also we can also create the keyhole mode, or at the same time deep penetration welding processes even using the laser. But point is that laser welding, it is not required to create any kind of the vacuum chamber, and another point is that laser welding does not create any extra X-ray production during the process. So, of course, if we compare between these two, the high depth of penetration can be achieved using the electron beam welding processes, and at the same time the precision of the joint is more in case of electron beam welding process, because it generally happens in a vacuum. So, without any contamination of the surrounding elements. So, that is the main difference from the laser. Now, what are the typical advantages of the electron beam welding process? So, advantage of the electron beam welding process, that maximum amount of the weld penetration is achieved with the least amount of the heat input, and that actually helps to reduce the distortion. So, in this case, of course, between the laser and electron beam, if we compare, the electron beam welding is the more preferred, but limitation is that other way, that it is a costly as compared to the laser welding process. Second point is that electron beam welding process may not be necessary always for the secondary operation. Secondary operation means, so to create remove the contaminated surface on the of the weld joints. That type of things is not required in case of electron beam, because electron beam can produce very clean homogeneous structure in a vacuum. So, that since this vacuum environment actually eliminates any atmospheric contamination in the weld. That is the biggest or main advantage of the electron beam welding process. Difficult to weld metals which cannot be possible in other welding processes, or dissimilar combination of the materials can be more preferred in case of electron beam using the electron beam welding process. So, of course, there are some difficulty or there are some issues of welding of the dissimilar materials using electron beam, but apart from that so many different types of dissimilar combination of the materials and difficult to weld materials can easily be done using the electron beam welding processes. And another advantage is the electron beam welding process is that extreme precision weld joint can be produced, because most of the cases it is controlled by CNC machines, and in that way it also reduces the scrap rate. So, all these advantageous points of course exist in case of electron beam welding process as compared to the laser, and there is a typical issues in case of electron beam welding process, specifically joining of the dissimilar metal. That we will discuss later on. But what are the typical application of the electron beam welding processes, specifically in industry? If we see that bimetal saw blades can be welded using the electron beam welding process. Transmission assemblies, we find out the application of the electron beam welding processes, and of course, huge application we can find out the aerospace components, where the precision of the joints and homogeneity in the structure is the main important factor. So, we can do the further on the electron beam welding process, and now we will try to discuss that what are the principle of the electron beam welding process. Of course, it is mostly it is known, but here we can see the summarize that what principle that electron beam welding process follows basically. First point is that the heart of the electron beam welding process is the electron beam generator from which the electron is emitted. So, that is called the electron gun or electron column. Second thing is that electron are generated. So, basically the electron are generated by the heating process, negatively charged filament, for example negatively charged filament, and 2 is we heated that certain temperature, that with thermionic emission temperature. So, at that temperature range electrons are emitted. Now, when there is a emission of the electrons, the machines actually control or accelerated this electron, so that the high amount of the kinetic energy of the electrons will be able to produce the amount of the heat energy. Now, next step is that once we can create that electron emission, and from there electrons are accelerated by the electric field of negatively charged bias electrode, because bias electrode helps to accelerate the emitted electrons, and that bias is present between the cathode and anode. If you see the picture also, that bias is basically present between the anode and cathode. So, after emission of the electron, then it is accelerated, and the next step accelerated, and then after that next step of the electron beam welding process is that the accelerated electrons is basically using the magnetic focusing lens, it is focused, and magnetic also the helps the magnetic, with the help of the magnetic deflection coils we can deflect the electron beam with the desired position. So, these are the basic steps. If we see in general that overall the generation of the electron and then acceleration of the electron, and the next second component, third component is the focusing of the electron. That means, it is the focusing of the electron, we can concentrate one specific point or specific line, and then another part is the deflecting of the beam of the electrons, and whether we want to put it want to focus at that point, we can put the electron beam. Next, when the electron beam is interact with the workpiece, so basically the kinetic energy of the electron beam is converted to the heat energy, and that heat energy actually creates the one deep penetrated weld by the formation of the keyhole. Now, if you see the in principle that electron beam can be focused under the vacuum basically and strikes the metal surface at a velocity of up to the maximum of 70% of the speed of the light. So, with this speed around 95% of the electron's kinetic energy is basically converted to the amount of the heat energy. So, in that sense probably the fusion efficiency of this process is relatively more. So, as compared to the laser welding process, this is also another advantage, the efficiency of this process is relatively more. Then electron beam can be focused on the diameter in the range of maybe 0.3 to 0.8 millimeter, that means 300 micrometer to 800 micrometers. Of course, this focusing can also be done using the laser process as well. And then one that with this focusing diameter, the concentration of the electrode can create high amount of the energy, and that energy is able to produce the deep penetration welding with the formation of the keyhole. So, we can see the laser welding as well as electron, both welding processes also can create the keyhole, and that keyhole actually helps to penetrate very high. So, that means when there is a requirement of the very high thickness material to be joined, then in that case electron beam welding process is the more preferable as compared to the laser welding process, because high depth of penetration is more easily controlled with the minimum heat affected zone or minimum fusion zone in by using the electron beam welding process as compared to the laser beam welding process. Now, if we see what are the keyhole formation mechanism in case of electron beam welding process. So, in this case the power density of this process is as high as 10 to the power 9 watt per meter square. I think it should be more than that, and therefore, high energy is concentrated, and mechanism of weld pool formation is definitely it will be different from the normal arc welding processes, but maybe almost similar to the laser beam welding processes. When the metal is heated to very high temperature, definitely it will, when it is cross the vaporization temperature, it vaporizes the material. So, therefore, when it vaporizes the material, there is a deep crater or hole is formed under the heat sources. So, when is the formation of the deep crater hole under the heat sources? So, but at the same time, when electron beam produce the deep hole, there is maybe some reservoir of the material may exist behind this keyhole. So, when the heat source is moves in certain direction, so that hole is actually filled by the behind that the molten material from the reservoir. So, and then it subsequently solidify oil bed, and this is the typical formation of the keyhole mechanism or keyhole formation in the electron beam welding process. We can see that further on the what are the mechanism of the keyhole formation in case of electron beam welding process. So, basically the forces which create the electron beam welding are, first there are three forces. One is the electron momentum of the electron, because it moves very high speed. Second is the vapor pressure, it creates the vapor, and that actually creates the vapor pressure, and of course, with the interaction of the electron beam with the material, and that also with the formation of the keyhole, it creates the recoil pressure. Therefore, when you try to form the in general, when you try to explain the mechanism of the keyhole formation, so that we can compare between these two, surface tension force of the keyhole formation surface tension force and the gravitational force. When they are equal, or maybe they actually, when they are equal with respect to each other, they actually opens the keyhole, makes the keyhole and keep live the keyhole formation, and that actually depends on the surface tension, in the balance between the surface tension force and the any other gravitational forces. So, of course, keyhole will be open, it may, because depending upon the these two forces, magnitude of these two forces and direction of these two forces decides whether keyhole will be keep open or it can be also closed. So, that can be better explained in terms of the how these two forces are balancing with respect to each other. So, in this case keyhole forming forces are much higher, so that keyhole keep opens during the process itself. Now, we can do the simple calculation that electron momentum pressure, here if you see that given by this expression P A equal to twice J M E V by E square. Here is the J is the current density, V is the accelerating voltage, and M is the mass of the electron. So, if you know all these parameters, so it is possible to estimate the momentum pressure created by the electron. But what are the control parameters of electron beam welding process? Of course, there are several control, like other welding processes or any other gas arc welding processes, several control parameters also exist in case of electron beam welding process. Just we can divide into two components, the primary variables and another is the secondary variables. So, primary variables is that filament current voltage and the travel speed, and the secondary variables is the beam focus, deflection of the beam, power supply, and of course, the vacuum chamber, or up to what extent, what pressure we can create the vacuum. So, all these are the secondary variables. Now, of course, with these variables, but primary variables actually more controllable variables, in the sense that there exists some interrelationship between the power of the beam and as well as the travel speed, and that actually decides the what is the amount of energy exactly is used for the welding purposes. But of course, the performance of the welding can maybe significantly changes by varying the secondary variables. The most important thing is that the depth to width ratio can be controlled by the beam focus and the deflection of the beam. By this, in these are the two parameters that actually influence the depth to width ratio. That means, basically depth to width ratio is decided, ultimately it affects the molten zone or the heat affected zone of this process. Now, we can see that the one is the typical electron beam welding machines. What are the typical components of the electron beam welding machines? Here see that cable, then the top, the high voltage is applied, then cathode that actually creates, emits the or creates the, it generates the electrons here, and the bias curve, that actually bias curve actually helps to accelerate the created electrons. Then primary anode and cathode, basically that they actually create the circuit in this case. And then electron beam, if you see the yellow color, that shows as the electron beam. So, after creating, it is accelerated, and then electron beam is put in the focusing coil, goes through the focusing coil. So, focusing coil helps to focus this thing and focus on a specific position, and then deflection coil also helps to deflect the electron beam, and finally, it is focused on the workpiece that actually kept as a vacuum chamber. And if you see that there is a observing system also there to see the position of the workpiece. So, these are the very typical and very simple way to present the typical components of an electron beam welding machine. So, we can do further on the electron beam welding processes the very simple or basic calculation. First calculation is that how to estimate the mechanical power of a beam of electrons. If you see the formula, that kinetic energy, the kinetic energy of the electron divided by T. So, power is the energy by T, that is estimated by half of m E into n V square into efficiency. So, basically here if you see this formula, that m E actually represents the mass of the electron that is given, and V is the basically velocity of the electron, that is of course it should be less than light velocity of the light. So, around 0.30% depending upon accelerating of the electron, it can be around 30 to 70% of the velocity of the light. So, if you see that V is equal to 0.3 to 0.7 times of the velocity of the light. So, velocity of the light into 3 into 10 to the power minus 10 to the 3 into 10 to the 8 meter per second, and n, since there is a time component here, we are estimating the beam power. So, here n represents the number of electrons, we can estimate in that way the number of electrons per unit time. So, that it represents the total kinetic power of the electron. Now, in other way, that heat input can also be estimated, that means energy input per unit length. So, it is basically by the unit of joule per millimeter. So, when you estimate the heat input per unit length, in this case the two parameters, what is the beam power and at the same time what is the speed. It takes the combined effect of the welding velocity as well as the power, welding power also. So, ratio of that is a measure of the heat input per unit length. So, that means here it actually decides for the same incoming power, if we use the high welding velocity. So, actually heat input will be less as compared to the when you consider the very slow velocity. So, basically very low velocity the heat input will be more, and very high velocity the heat input will be the less, even for the power remains the same. So, that is why it takes the effect of the welding velocity also. So, here if you see the efficiency into volt into current divided by the welding speed. So, V is the beam accelerating voltage, I is the beam current, or V equal to small v equal to actually travel velocity, that means welding speed, and capital P is the power of the beam. So, that also equivalent to the volt into amps, that means volt into current. So, power is represented watt or joule per second, and another efficiency term also given in this case. So, these are the basic calculation, we can find out the kinetic energy of the electron or maybe kinetic energy as well as the power of the electron. Basically we can estimate here, and what is the how to estimate the heat input per unit length in case of electron beam welding processes, or specifically I can say that this formula for heat input not only electron beam welding process, maybe in other arc welding processes also we can use the similar kind of formula. If we know in that arc welding process what is the voltage, what is the current is using, and what is the welding speed. So, this is the heat input per unit length is one of the typical characteristic parameter that actually takes care of the welding velocity. Now, what are the effect of the different variable on the weld bead geometry in case of electron beam welding process? So, first is the accelerating voltage. Of course, accelerating voltage is increased, the depth of penetration will also increase. So, then that means when accelerating voltage is increased, that means the electron is accelerated more, that it will can create over a small focus zone the high amount of the heat energy, and that always helps to create the more penetration of the material. But of course, the accelerating voltage and the velocity of the electron having some limitation, it can goes up to the maximum of the around 70% of the velocity of the light. So, that is why the accelerating voltage, in general accelerating voltage, actually increasing the accelerating voltage, increasing the penetration. Now, beam current for any given accelerating voltage, the penetration will increase with the beam current. Of course, other way also, if we increase the beam current also, it also helps to increase the total amount of the beam power, and in that way that actually creates a more energy that can be released on the workpiece, and finally it influence the penetration of the welded joint. Next is the travel speed. Travel speed, basically understand that if travel speed is more, the amount of the heat input to the workpiece surface actually decreases. So that, or if travel speed is very low, that amount of the energy goes to the workpiece surface, that actually increases. So, with respect to that point of view, that weld bit will become narrow and penetration will decrease as the travel speed will increase. So, travel speed will increase means less amount of the energy, that will decreases the penetration. But at the same time, when it is decreases the penetration, and that it will try to narrow down the weld width. But if travel speed is very low, it can, the width can be that, in that case it is beneficial, both it will try to increase the width as well as penetration. So, these are the basic idea about the effect of the travel speed on the weld bit geometry in case of electron beam welding process. So, of course, another parameter that actually influences the weld bit geometry on the electron beam welding process, that is the beam spot size. So, basically very sharp or small focus beam will produce the high power density on the surface. Definitely high power density will produce very narrow and high depth of penetration and geometry. Of course, parallel sided geometry means almost it is a kind of cylindrical shape kind of geometry without much variation from the top and the bottom. That type of typical geometry is possible to in case of the electron beam welding process. But in that case, the beam spot size should be the very small. Okay. If beam spot size is bigger, probably it may not be the variation of the from the top to the bottom, there is must be some, it will try to the weld pool geometry is gradually decreasing. The width, actually size of the geometry, cross section of the geometry from top to the bottom is gradually decreasing if beam size is bigger. So, other way, the beam spot size actually decides the power density on the surface. So, in that way it will try to impact on the size of the weld bit. Now, in general, if you see the what are the typical advantages of the electron beam welding process, here you can see that accurately controlled energy density is basically possible in case of electron beam welding process. So, that may not be possible in case of other arc welding processes, and to some extent it is possible for the laser welding process. But in electron beam welding process, it is more controlled energy density is possible to produce, and of course, very small beam size can weld very thick material. So, if you think that 0.025 very thin to very thick material. So, there is a wide controllable electron beam energy is possible. So, that means it can be possible 0.025 millimeter welding of the 0.025 millimeter material, and of course, in this case we need to control the electron density or energy input to the substrate material, but at the same time it is possible to produce 300 millimeter. So, huge thickness is possible using the electron beam welding processes, that may not be possible in case of other arc welding processes or in using the laser welding process. Next point is that very accurate beam alignment at any position is possible using the electron beam welding process. Therefore, the two base metals of the, it is a very control the melting of the base metal in the selective way, so that when you try to join some dissimilar materials, that actually helps to produce the weld joint and increase the metallurgical compatibilities. So, in that way it is very advantageous in electron beam welding processes when you try to join the specifically dissimilar combination of the materials. The third advantage is that since low total heat input produces the narrow bead and the heat affected zone, as a result low residual stress and minimum distortion is possible in this case, because heat affected zone, a narrow heat affected zone and narrow oil pool zone can be created in case of electron beam welding process. That actually helps to reduce the distortion with minimum possible distortion and very low residual stresses. So, associate with the metal, so certain material, because most of the combination of the dissimilar materials is difficult to join in other welding processes, because there may not be the metallurgical, there are the issues of the metallurgical incompatibility between the materials. So, that incompatibility of the metallurgical incompatibility of the materials can be controlled using the electron beam welding process, and sometimes this can be done using some filler materials also. But the joining of the dissimilar materials is maybe can be done more controlled way using the electron beam welding process. The main advantage is that we use the vacuum environment when you try to join the workpiece material, whether it is similar or dissimilar materials, using the electron beam welding process. Therefore, having the minimizes the effects of the surface contamination of the metal by oxygen, nitrogen and hydrogen, which is typically present in any arc welding processes or even for the laser welding processes. So, that contamination from the outside atmosphere can be minimized using the electron beam welding process. That is the biggest advantage in case of this process. Dissimilar material combination, already we mentioned that, involving the high thermal conductivity metals such as copper can be welded using the electron beam welding process without any preheating. So, normally any other arc welding processes or laser welding processes, when you try to join the high conductive material, so like copper, most of the cases we use as a preheating the surface, and then we can do the main source of the energy in terms of laser or from the arc welding process, and normally in that way we can do the welding of the highly conductive materials. But in this case, in electron beam welding process, we can do easily without any preheating sources, the welding can be done. So, that means in general the advantage of the electron beam welding process is that the dissimilar combination, highly reflective material and highly conductive material can be joined more easily in using the electron beam welding process, which may not be possible at all in other type of welding processes. But of course, there is certain other disadvantage or negative points of the electron beam welding processes. We will try to see that what are the disadvantage of this process. First is the, of course, high heat concentration. So, rapid solidification may happen, and this rapid solidification also produces a different type of the structure, and finally it results in the most of the cases we can find out the brittleness of the weld and several other defects, and porosity, crack may form due to the rapid solidification. This is the one disadvantage. And second is that using the, since electron beam welding process, the using the vacuum chamber, that actually the all welding process can be done in the vacuum chamber. So, because of that it actually reduce the product size and limit the product design, because vacuum chamber may not be created for a large scale welding process or very big component. We try to weld in a small part, it is very difficult to separate out, keeping the separate out of this only for small part for a large component, to create the vacuum there and doing the electron beam welding process. So, that is the one biggest advantage of the using the vacuum chamber. Another thing is that since electron beam is easily deflected by the any other electrostatic and magnetic field, specifically it is important in case of dissimilar material. So, That is the other way. We will discuss this issue, that when you try to produce the dissimilar materials, how what are the difficulty of application of electron beam welding process there. Another is another limitation of the electron beam welding process is it should be the electrical conductivity of the materials is required. So, non electrical conductivity material is not having any electrical conductivity, we cannot apply these materials for electron beam welding process. High precision of the seam preparation, probably when you try to joint the material, then high precision maybe fitting of this material is required to produce the successful weld joint using the electron beam welding process. So, other way that X-ray actually forms during the emission of the secondary electrons from the workpiece. So, that is another equation we should consider during the electron beam welding processes, that is absent in other welding processes. That is one of the important disadvantage of electron beam welding process. And finally, of course, this machine is very costly. So, cost is the main limitation of the application of the this welding process widely. Of course, apart from all these disadvantage, and we can stick with the advantage, very precision, even if we compromise with the cost in other disadvantage of the electron beam welding process, still it is a very good solution, specifically for the very high thick material and several dissimilar combination of the materials. Now, try to focus on what are the electron beam welding processes for the dissimilar combination of the materials. We can see the dissimilar combination of the materials, there are several issues. So, we try to discuss this thing, that there is when you try to join practically the two dissimilar materials, if you look into the picture itself, that material A and material B, two different materials. So, their physical and thermal, electrical, all these properties will be different, these two materials. So, we found out that the difference of the specific, if there is a difference of the, since there is a difference in the material properties between these two. So, most of the case dissimilar combination of the materials, the beam got deflected with the towards certain material. So, if we see that figure, in this figure, that we started exactly the putting the focusing on the electron beam on the interface between material A and B, but if we look into throughout the depth of this penetration, that gradually the beams being deflected towards one of the materials. So, that actually creates the insufficient joint between these two dissimilar combination of materials. But what is the physical sense or physical reason for this kind of deflection? So, this is one of the typical problem of the electron beam welding of dissimilar materials, but this beam got deflected, not always necessary that high amount of the deflection will happen, maybe some certain combination of the materials, the deflection can be also very small. But anyway, since the material properties are different, so definitely we will be getting at least some amount of the deflection of the electron beam. So, what are the typical reason of the deflection of the beam within this along the depth direction of this material? First thing is that residual magnetism may be one of the reason of weldments in their fixture. The residual magnetism may exist in their fixtures in case of ferromagnetic materials, and because during the welding the beams get deflected due to the electromagnetism creation during the welding process. That is the most important things when you during the joining of the dissimilar material. So, what may be the other reasons for the beam deflection? Another point is the thermoelectric magnetic field caused by the temperature gradient. Of course, the thermal properties between these two materials are different. So, it may not be the single point, there must be some temperature difference between these two materials at the specific point. So, that temperature difference as well as gradient. So, that temperature gradient to some extent influence the thermoelectric magnetic field. that is typically known as the Seebeck effect. So, that Seebeck effect is responsible for, in this case, joining of the dissimilar materials for the deflection of the beam. Another point is that sometimes the electric currents on the wall of the vacuum chamber of an electron beam welding process, actually when the electric current interacted with the electron beam. So, that also is responsible for the deflection of the beam. So, these are the typical 3 basic reasons that the deflection of the beams happens, we observe in case of the electron beam welding process for the dissimilar combination of the materials. So, we can see that if we analyze that the electron beam welding of the dissimilar materials. So, here we consider the 3 different sets of the dissimilar materials, that is say for example, we want to join between the iron and copper. Second is the stainless steel SS304 and the low carbon steel. And third is the low carbon steel and nickel copper alloy. So, all these 3 dissimilar combination of the metals, if we try to join by the electron beam welding process. So, ideally what will happen between this. So, before doing that, we will try to look back the what is the Seebeck effect. So, Seebeck effect is the, it is a phenomena of producing the, actually produce the electromagnetic force and consequently an electric current in a loop of material consisting of at least 2 dissimilar materials when the junctions are maintained at 2 different temperatures. So, that different temperatures is basically creates the Seebeck effect, but Seebeck effect can be represented that is a, in general the conversion of the heat directly into the electricity. So, that heat is comes in terms of the temperature gradient. So, EMF, the electromotive force, can be represented minus S into delta T, where S is the coefficients and delta T is the temperature gradient. So, basically the presence of temperature gradient actually creates the some electromotive force, that is the Seebeck effect, and that effect is basically responsible here to create the deflection of the beam. So, we have analyzed these things, that combination of these 3 materials, and if you see that materials 1, 2 and if we roughly estimate the deflection angle, if you look into this figure. So, beam is deflected towards the material B. So, during the dissimilar combination of the materials, it is important to know that the beam will be deflected in which direction, whether towards material A or towards material B. If we know the deflection of the beam, probably there may be some solution to stop this deflecting of the material accordingly, or maybe other way we can initially put the focus on the beam to compromise the minimum deflection of the beam, or maybe you can minimize the deflection of the beam. So, if we analyze these things, that which material it will be deflected. So, look into the table, that combination of these 3 materials. So, if serial number 1, that iron and copper, if we estimate that deflection angle is around 2.86 degree. So, of course, the deflection angle is very small, and this deflection is depends on the properties, and the basically this analysis has been done only considering the there is a Seebeck effect. Now, deflected direction, that means deflected direction means the beam will be deflected towards the iron if we consider the combination of the iron and copper joint. So, beam will be deflected. So, for example, the material A should be the copper and material B should be the iron in this case. So, that beam is deflected towards the iron in this case. Second combination, and we can see that stainless steel and low carbon steel. Here we roughly estimate the deflection angle is around 2.5 degree, although it is a very small, but beam will be deflected in this case towards the low carbon steel. That means, in this case the material A is the stainless steel and material B is the low carbon steel. Third is the low carbon steel and the nickel copper alloy. So, nickel copper alloy, if you see but in this case we estimated the deflection angle is very high, it is around 8.5 degree as compared to the other combination of the materials. But in this case also beam will be deflected towards the low carbon steel So, material A should be the nickel copper alloy and material B should be the low carbon steel. And we have see there are some simulated results also, that if you see the color, highlighted color between these two, the it's a simulation has been done between the nickel copper alloy and right hand side is the low carbon alloy. So, here if you see that beam is deflected actually towards the low carbon steel. So, from that simulation it is obvious that there must be some deflected if we correctly consider the in the Seebeck effect in all these cases. But if we look into all this combination and we will try to look into that, what are the higher side Seebeck electromagnetic force, Seebeck EMF will be generated. All these three cases, if you see the first cases in iron, second case is low carbon steel and the third case is also low carbon steel, the higher side of the EMF generation and higher relative permeability. So, basically the magnetic permeability, since the magnetic permeability of these materials are different, that actually helps to create the beam deflection. So, in this case if we see the higher relative magnetic permeability are basically higher side more in case of iron, first cases, second cases also low carbon steel and third cases also low carbon steel. So, higher EMF generation and the high amount of the relative magnetic permeability of all this low carbon steel and iron. So, that is why all the cases we found out that beam is deflected either in pure iron or beam is deflected in the low carbon steel, because the permeability, relative permeability is more for all these three materials. So, this is the way if we know that about the materials, combination of the materials, and we can roughly estimate what is the beam deflection angles for a towards the specific material when you try to use the electron beam. So, if in this figure also another point out that this figure, the red zone actually represents the depth of penetration. That depth of penetration, we can see this type of depth of penetration can be created using the electron beam welding process. So, this specific size is entirely different from the laser welding processes. So, after discussing this typical issues in the dissimilar combination of the material welding using the electron beam welding process, now we will try to overall try to compare between the laser and electron beam welding processes, because in this module we will covering only the laser and electron beam welding process. So, let us see in a summary that what are the difference between these two processes. First is that what are the different perspective is the first is in terms of the weld zone and the heat affected zone. So, in case of electron beam welding process, it is a very narrow, very small weld zone, smaller in the sense it is a very narrow, but it can create the high depth of penetration. Laser welding also we can find out the narrow and smaller weld zone. So, very narrow weld zone and but depth of penetration is less as compared to the electron beam welding process. Second point is the penetration. Of course, penetration, deep penetration can be possible in case of electron beam welding process, little low penetration welding, low lac penetration can also be possible in the normally in case of laser welding process. So, in this case if we compare the depth of penetration in this electron beam welding process is more as compared to the in general laser welding processes. Welding speed, very high welding speed can be used in case of electron beam welding process, but as compared to the electron beam welding process, the speed of the laser welding process is less, because if you take the too much of high speed, that actually may not stabilize the keyhole formation in case of laser welding process. So, there may be some limitation of the welding speed we can use depending upon the other combination of the primary and secondary variables we used in the laser welding process. Shielding gas, electron beam, since electron beam is produced in the vacuum chamber, there is no need of the shielding gas in case of electron beam welding processes, but laser welding process to protect the molten pool we generally use the shielding gas, either nitrogen or argon. This is the typical shielding gas can be used in case of the laser welding processes. Vacuum chamber, in terms of the vacuum chamber. So, electron beams welding process, there is a, of course, there is a need of the vacuum chamber, otherwise the beam control of the beam may not be possible, and laser welding process, that is the advantage, we do not need any kind of vacuum chamber. So, in a large scale welding process or very big component, when there is no limitation of the size of the vacuum chamber. So, in that case laser welding can be a better solution as compared to the electron beam welding process. Cost, of course, electron beam welding process is very costly process. So, cost is very high. So, that is the main limitation of the electron beam welding process, but in laser welding process comparatively low as compared to the electron beam welding process. Generation of the X-ray, in that perspective the electron beam, it is possible for generation of the X-ray, but laser welding even it is not possible in case of X-ray generation. Now, the biggest advantage of the electron beam welding process is that in terms of the efficiency. If we see the efficiency of the electron beam welding process around 80 to 90%, but in that case laser welding is the less efficient, 10 to 20%. So, there is a basic difference between the electron beam welding process and laser beam welding process. Size of the workpiece, there is a limitation of the size of the workpiece in case of electron beam welding process, and it is limited by the size of the vacuum chamber, but in that case laser welding, the size of the workpiece material, there is no limitation. So, that means for a big component, if you want to do local welding process, so probably it is more easier to apply the laser welding process as compared to the electron beam welding process. So, by this we have tried to discuss about the laser beam welding processes and electron beam welding process, and what are the typical issues and what are the recent advances in case of laser or electron beam welding process. We will try to cover through some basic knowledge of all these processes. So, thank you very much for your kind attention. This is the end of the module 2. Thank you.